thank you for joining us on another episode of Low Pressure Area, a podcast from Campbell Scientific. I'm Jamie McDonald,
I'm Richard McKay.
and today, Richard, we're going to be talking about sea-air gas exchange, which might not mean very much to many people straight off the bat, and that's kind of the point. Is we're going to be digging into what it actually means, why it's really important for the world, and I think this is actually a topic that is more important and more interesting to people than they perhaps think. To help us pick it apart, dig into it, and understand it, we're very happy to welcome a special guest this week. It's Dr. Fabian Lange, who has done his research at the Max Planck Institute for Marine Microbiology and focused on transport processes in the water column, which again sounds like, oh man, how do we dig into this? But Fabian, I think you're going to really help us to understand what all of this means and make it accessible to everyone else. So welcome to the podcast. It's great to have you.
Yeah. Thank you for having me. Thanks for the nice introduction. Very happy to be here. And yeah, I'll do my very best to give some input on that topic and see if I can answer some questions as well. I hope so.
Yeah, I'm sure you can. And, we were saying before this as well, that this is a topic that Richard and I know some bits about, and we've certainly got our own questions that we'll be asking you. But we're looking forward to understanding a bit more about exactly what your research was on and helping everyone else listening to understand better what we're actually talking about. So, often we start our shows by talking about the basics of the topic that we've picked, going back to kind of first principles and understanding, okay, what are the key concepts here? And there's a lot, I think, of key concepts with this one as well. But carbon uptake, I think, is probably a good place to start. So what is carbon uptake? And how does it fit into this whole discussion on sea air gas exchange? What is the gas that we're talking about?
Yeah, that's a good question. So carbon uptake mostly relates to CO2, so carbon dioxide, which is a main greenhouse gas in our atmosphere. And when we talk about carbon uptake, then obviously the first thing that pops into our minds is probably like plants. They do like photosynthesis. They take up carbon, assimilate it, put it into their biomass. So that's a type of a carbon uptake. But then, of course, we also do have other carbon uptake processes, so to say. For instance, like with water bodies, which is basically like a liquid, and liquid can also store gases. So gases can dissolve in liquids. They have a solubility depending on which gas they can solve better or not so good. And carbon dioxide, for instance, is also something that can be dissolved in a liquid. You usually have it like with sparkling water, right? When you open it, it's just carbon dioxide that just comes out, so you can hear the gas coming out of the water basically. But there's also like a natural equilibrium, so between the atmosphere and water bodies. So, and that's kind of the sea air gas exchange that we're going to talk about today. So if you have a certain amount of CO2 in the atmosphere, a certain amount of that will dissolve in the water column. And if you put more than in the atmosphere, then there will be also more dissolving in the water column as well. So, and that's then the transition. You can have it also the other way around. So if you have a lot of CO2 in the water column and then the atmosphere has less, then the equilibrium would allow, so to say, then the flux of CO2 would reverse and it will go up into the atmosphere. So just a very, very broad explanation of what we're going to talk about. Yeah.
Yeah, and that's really interesting, I think, to point out. And you said this to me before, that I think a lot of people, when they think about carbon sinks or places that store carbon dioxide, we often think about forests. And, there's been how many different kinds of tree planting initiatives with this in mind. But actually, the sea and the oceans are an even bigger carbon storage, right? I think we can talk about this again a little bit later, but I think often people forget that it is possible for gases to be taken up into water bodies as well. And I liked your example there of sparkling water. Obviously, right? When you open a bottle of sparkling water, that's exactly what's happened. You mentioned there a little bit also about fluxes, and I think they're key to this discussion. What is a flux? How do we describe it?
Yeah, so quite a bit of my research was around, rates and fluxes. So, and I had a lot of discussions around what is what actually and how to explain it best. Don't think if I have the best way of explaining it yet, but I always try a different way. So today I'm going to try another way. Um, so flux is basically, before I dive into the explanation, is something. So if you have high concentration at one point and a low concentration at the other point, then you always have a flux from the high to the low concentration, just by molecular laws, so to say, diffusion processes. They always tend to equilibrate, evenly in space, so to say. So that's basically flux, and I try to come up with a with a comparison that makes maybe more visible where the difference between rate and fluxes are. Um, so if you picture me like in my house behind the door, eating apples, so then I consume apples, right? So and I eat a lot of apples. I do like them. So that's basically the rate. Let's say I eat 10 apples per day in my volume. So I am the volume, so to say. So then then the rate would be 10 apples per my volume per day. So that's a sink for apples, right? So I need to get more apples from somewhere because else I can't continue eating apples, right? And then the rate goes to zero. So to maintain that rate of 10 apples per day, I need 10 apples coming through the door to me, right? And the door is an area basically, right? So that's then the flux coming through this area to me, feeding my rate, so to say. So that's the fluxes, and the other one, me, is the rate, so to say. I don't know if that helps to understand. We can make it a bit more complex because obviously I would be the volume of lower apple concentration. Ridiculous, but yeah. Um, and outside, there must be a volume of more apples, right? Like higher apple concentration. And that's the supermarket, basically. So if there's a supermarket very close by, then it's easy, for someone to bring the apples to me, so to say, right? So to have a constant flux from the supermarket to me with apples, 10 apples per day. But if the supermarket is now, that's not a problem. So if the supermarket is now, I don't know, 12 hours away, then it's a very long distance, right? So it's hard to kind of maintain this flux of 10 apples per day because you always have to go back and forth just to deliver the apples, so to say. It has some caveats, this comparison, but what what I want to address here is the length between the source of apples and me. So if you increase the length between source and consumption, that affects the flux as well. And then another thing that also affects the flux is the amount of apples at the source, which is the supermarket. So if the supermarket runs out of apples, it might happen that I have suddenly more apples than the supermarket. So the supermarket would demand the apples from me. So then I would, basically maintain a flux towards the supermarket until I also run out of apples while I'm still consuming the apples. So they will be consumed more rapidly, and then the flux dies out because we don't have apples anywhere. So we don't have flux in this region, so to say. So the concentration difference of apples between the two spaces, that's the second factor that affects fluxes. And then we have a third factor, which is the size of my door. So if it's, a door where an apple would fit through, I hope should fit through it. But then it has more area to migrate through, so to say. But if we make the door now very small, so only one apple at a time can go through, then this would inhibit the flux as well, because it's not possible to bring more apples through at the same time. So that's the third factor. It's the area over which the flux takes place. So we have the area that is important over which the flux takes place, concentration gradient, and the length of the distance of the flux, so to say. Yeah.
Okay.
Just maybe
Flux
that's flux.
flux in a way is also simply change, isn't it? And temperature as an example, as you were saying, a lot of systems in the atmosphere, they try to reach equilibrium. So if you have a hot temperature in one spot and cold temperature somewhere else, that will try to equalize and be a constant temperature of 15 over that entire area instead of 25 here and 10 over here. Oh, I'm sorry, you don't see my hands, but one hand to the other. And so similar sort of idea to the apples, that exchange. And as you were saying, sort of if you reached equilibrium, there might not be any flux because you had 10 apples on one side and 10 on the other side, and you'd already eaten 10 all that day or something. So, then it might not be necessarily any change because of that. But yeah, maybe I'm muddying waters. But at its principle, I'll say flux is used in a lot of general terms for a change, that there's a variance, let's say. But yeah, nice way to describe it, though. I've not heard the apple analogy, so I like that one. So,
Yeah, I
Works well.
tried to explain it previously with a piece of paper, and then just say you have a flux going through that paper. So the
right.
paper is the area, and then below you have the rate, and then the
Mm,
paper at the same time is the surface of the water. So
mm,
that's kind of how I try to explain it in, like, I don't know, classes or courses,
sure.
about
Mhm.
fluxes, because it's more related also to the sea air gas exchange that we're going to talk
Right.
about. But
Right.
yeah, I thought maybe the apples is a bit easier to explain than also the three factors that affect fluxes. Yeah.
Absolutely. And
Definitely.
so I'm going to jump in one more time. That that term for the area, is that also known as a footprint? So that's the terms used in, for example, land fluxes of greenhouse gases and other trace gases. So I'm curious if it's the same term and it has the same sort of challenges with it. That has to be homogeneous, or would you only use a certain size if it's calm, for example, on the ocean? Sorry, it's probably going into too much detail in one spot, but just a curious point when you're mentioning it.
So I wouldn't say it's the same because the footprint just explains the origin of the flux that you're measuring, but you give the flux per square meter usually, right? So
Okay.
that's the area. If you would then change the flux to a hectare, then of course
Sure.
the unit changes, but then the value
Mhm.
changes as well. But the
Yes.
footprint only tells you from where the flux comes from. Guess you think about like eddy covariance footprints, for instance. So that's basically a probability density function, right? So
Mhm.
yeah, I don't know. We can talk about it maybe over the episode a bit, but it's broadly spoken. It just tells you from where the flux came that you measured.
Okay.
So yeah,
Thanks.
And I
yeah.
no, it's a really nice way to introduce the topic, and I think, as you say, it's very easy also to get very scientific very quickly. And I think that's half
Yes.
the point of what we want to discuss today is to get into that depth as well, but from a perspective of exactly the sea or oceans as opposed to land, because this is a topic that Richard you brought up, right? We measure fluxes on land quite often as well, but the importance of talking today about fluxes across oceans and on seas is the importance of carbon dioxide in that system. And I think, Fabian, you said to me at some point that the ocean contributes, what did you say, 21 trillion US dollars to human welfare generally across the world. So it has a big impact on us, and that 60% of that benefit can be traced back to the coastal regions. Am I right in saying that it's these coastal regions that are the most interesting, at least at this point, for us to be measuring or understanding the sea air gas exchange, particularly when we're talking about carbon dioxide? So that either uptake of carbon dioxide into the oceans from the atmosphere, or then the reverse, which can happen as well, as you said.
Yes. Yeah. So I mean, obviously, I think coastal oceans are very interesting because that's what I wrote my PhD about, right? So other people might disagree here. Um, but yeah, so this 21 trillion, that's basically from a study, I think from the late 90s, 97 or something like that. So then these values might have changed a bit or reevaluated, but it's a nice value to orient. Um, yeah, and 60% of that relates to coastal systems. And this value, it's, yeah, how to say, it's a bit like ecosystem service. That's, I guess, a term that is used a lot these days, that you want to quantify the value of a system. Well, we can talk about it morally as well, if it's nice to talk about the value of a system in dollars, like a
Sure.
natural environment. It has also, I think, some things that are hard to put into value, right? Just for instance, if you take forests, just keep going back to terrestrial systems, but we could also take the ocean. Everyone loves to swim in the ocean, to do vacations at the oceans. That's also a value. Because we recover there, we enjoy the environment, but how to put that into money numbers, that's also difficult, and I'm not quite sure if that's also the right way to do it. But I understand that there's a need to quantify certain things. So what they did is basically looking into what economical value do we get out of it, kind of. And fishery belongs to it, for instance. Sand
Hmm.
mining belongs to it. The turnover of nutrients, for instance. So if you have like nutrient input from agricultural systems, from industry, but also from, like cities, wastewater and everything, we need to supply a certain energy or a certain, energy to kind of process it, to clean it from all the nutrients and everything that we put in there. And the ocean is doing that as well somehow, without a cost for us. So what they did is quantifying roughly how much of these nutrients are kind of buffered by these systems. And by buffering, I mean how much work do they do that we should have done, and what would
Right.
that be worth? So that's how they came up with this number, and that then also explains why 60% relates to coastal systems, because I mean they are in between the open ocean and the terrestrial systems. So they are the ones who receive the load first, so to say. So they have also, if you want to look at it this way, the opportunity to gain a lot of these 21 trillion US dollar per year. Yeah.
Makes
Yes,
sense.
that's where the number came from. Yeah.
Yeah. And with relevance then to what we're talking about here with the sea air gas exchange, is it right to say that these coastal regions are also often the focus of research, partly because of exactly there's a lot of benefit that comes from those shallower regions, but from the science perspective as well? Am I right to say that carbon uptake from the oceans is more efficient in shallower waters around coasts, or am I making that up completely?
That's a hard question to answer. I'm not quite sure if I can answer it in the very end, but I can I can tell you how to look at it, to create your own opinion about it.
Okay.
So part of the value that we just mentioned is also the CO2 uptake, and that accounts for 190 billion US dollar per year for
Wow.
coastal systems. And it is interesting because the ocean, I mean, covers two-thirds of our planet, right? So it's basically, we have a blue planet. So if you look on the Pacific, there's a certain angle in space basically where you only see blue. So it's just water. So obviously it's an important system on our planet, while the coastal regions are, very very narrow. And then we have to also, maybe I should explain that first. There's because we're talking now randomly about coastal oceans, and there's a lot of scientific literature as well where they used different definitions for coastal oceans, like distance from the shore, or some define it via depth. So you always have to be very careful if you want to look at into these systems, and if you want to compare numbers, especially because they often refer to different areas. So, but there is one definition I think everyone kind of agrees on nowadays. That's continental shelves, because continental shelves are kind of the area of the ocean that goes out into the sea until we have a water depth of 200 meters. So that's kind of the arbitrary border of shelves. And everyone who talks about continental shelves usually refers to that one. If not, they specifically state that. So, and then coming back to the entire area, why this matters, this coastal ocean or continental shelves cover like around 7-8%, varies a bit because it's hard to define the exact border also on the land side. Yeah, we can also talk about that. There's tons of things that we can talk about it. It's hard to kind of cut the border on the land side and on the sea side exactly. So it's 7-8% of the entire ocean are continental shelves. So it's a very small piece, but they are very important in carbon dioxide uptake. So they do get a lot of nutrient input from the land, as I said before, which kind of fuels, the primary productivity. Then you have usually also very shallow water, so there's a lot of light also going through the entire water column, basically. So there's a lot of opportunity, so to say, for primary producers throughout the entire water column to do photosynthesis, which of course fixes then carbon dioxide. Um, and that kind of creates a partial underpressure of CO2, which then forces CO2 to gas into the water, and that's then the flux of CO2 into the water column. So yeah, that's why coastal systems or continental shelves are very important. I could just continue
And also
for
possibly easier to measure as well because they're, I mean, it's still challenging, but maybe not I don't know, maybe is it easier to instrument or to measure that sort of coastal shelf area than maybe out in the open ocean without sight of land, for example? And would the measurements be more challenging because, like you're saying, there's less photosynthesis? Maybe I'm assuming, even though there'd probably still be a certain amount in that top layer, but and maybe other factors like the roughness or other factors of the interaction of the ocean and maybe even the air affecting that carbon and even sources of where it is and how that is distributed around the planet. I don't know. I'm not obviously the expert in this area, so it's great to have you on the show, Fabian. But yeah, just some thoughts that came up when you were talking about that.
Yeah. So you mentioned it's easier to measure it in coastal areas, right? So that's how I understood it, at least. I think, yeah, I would agree. At least it's cheaper because it's easier to access, right? So if you want to do measurements in the open ocean, obviously you need research vessels. So, and it's expensive to maintain them, usually like um, the more industrialized countries who have like a bit more wealth, they have fleet of research vessels. But for other countries, that part of the world, they don't. They simply don't have the money to maintain, professional research vessels, which, mm, of course, then also creates a bias in research, which is actually also very important for a lot of research. You need, if you want to scale it up then to a global scale, so to say, you need rates and fluxes and measurements and everything from all around the globe, right? So because especially if you look into rates from which you then want to derive, for instance, fluxes or whatever, or just budgets of a certain substance like CO2, for instance, rates vary depending on where you are. If you're in a tropical region, if you're in a polar region, you have different rates because there's just tons of different factors affecting it, temperature, nutrient availability, salinity, and so on. There's a lot of things, oxygen as well, but different topic. Yeah, so there's a measurement bias as well, where the which parts are better studied than other parts. Obviously, research vessels do research cruises all around the globe. So German research vessels do cruises in the Pacific, in the Atlantic, Indian Ocean, everywhere basically. But of course, they cannot really cover all this area and volume as you could, for instance, for coastal regions. So yes, we have a lot of research facilities in Europe that focus on marine research, and many of them, because it's easy to access, you just need a small boat that you can just rent or even buy. Just go out a couple of 100 meters or maybe a kilometer or whatever, do your measurements, come back same day. That's not a problem. So these regions are heavily studied. So you have a lot of values around those, while you have very little values in other regions. So yeah. So in that aspect, I agree.
Is there normally you'd be looking for example, a weather station? If it was a nice level surface, there weren't a lot of local factors, so new sources of water, different textures, different roughness, a change uh, in geography, that's where you would say, here's my reference station. And then when I look at all of how the rate of change of temperature or of wind or these other things or cloud development, when I go to a mountain site, then that's going to be a different environment, but I can see how it's different to my reference. When I go to a area of large source of water, then I would see how that's different to that reference. And so I'm curious if there's when you're doing, this carbon uptake in the ocean, is there a an ideal place to make that measurement that then you look at, the exceptional conditions where maybe there's higher tidal ranges or there's more industrial areas or there's maybe richer in the Caribbean or equatorial regions? Is there much more, light and more continuous 12-hour sunlight and warmth or something like this? So I'm just curious if there's a particular area that's sort of used either because of lack of data generally that's the reference or the ideal case, or does that simply not exist in this domain?
Uh, yeah, that's a very, very interesting question. But before I'm going to say anything about it, you mentioned that you have this similar reference system for cloud formation. So what is the reference system there? Like,
Well,
just I'm
I think,
curious now about it
yeah,
because I like
I,
clouds as well.
I guess you would when you're looking at either models from whether National Weather Services, they would try to use an ideal situation, so not introducing any local factors generally, and say, given this plot of land and it's flat and it's grass, for example, we know that the physical processes are like this, and therefore the temperature gradient changes when you go up by this much. When the wind goes across it because of the roughness and the color and other things, and maybe the amount of solar radiation and development of the boundary layer, then it changes a certain way. So you would apply that sort of concept to a parcel of air, call it 1 kilometer by 1 kilometer. And then when you move to some other area, a coastal area or a mountain or something, you would have to modify it or say these are the other changes that are introduced when we go to this area. So we need to modify it to do this and measure it and understand the differences really to that ideal homogeneous terrain, if you will, rather than sort of an outlier area. And so I was curious with this, again, maybe my knowledge is a little bit dangerous in eddy covariance, but again, going back to land measurements of eddy covariance, you try to not introduce local sources of advection from a mountain or anything else, and so you would try to use an ideal sort of site that has that you don't have a lot of influences that you can't account for. And then once you've understood the processes there, then you can start to look at other areas and then see what the differences are and understand the modifiers that are happening. And that's where I was trying to translate it to that ocean domain, if that helps make it better.
Yeah, what that was very nice explanation. Yeah, yeah. I try to separate it a little bit in my brain at the moment into because I feel it's two things that you can get out of that. Because on the one hand, like I understand you want to have, like this ideal system where you have like ideal processes where you know how it should look like and stuff like that. And based on that, you can then also, analyze the data that you get from other systems that looks similar to see, differences and then start to, predict certain processes and everything. So that's done, I think, everywhere. But then the other thing that you mentioned with the eddy covariance that you try to avoid, for instance, advection, if you have like hillsides or whatever, um, that's I would put more on a methodological side because that's basically a caveat of the method because eddy covariance is neglecting, so to say, the advective flux, right? So it doesn't mean that it doesn't matter, right? It's just in the system it might matter, but you don't want to capture it with this method because the method is not very good in resolving this process. So I think these are two levels, so to say,
Mm.
So on the one hand, you want to have for your method a nice place where it's appropriate to be used, so to say. And on the other hand, you need information of the system anyways. So if you don't have a better method yet, then you're still going to use, in this case, eddy covariance because you need to get a handle on the mechanisms behind processes, and that's also what I always liked, like during my PhD, to look in to get a lot of data for like around one topic, from a lot of different perspectives, as many as you can get. So also, if you get, not a ton of data for each method, but you have a ton of methods. So you have a lot of different perspectives and then try from that understand the mechanism behind the processes that you're looking at. And then after you understood the mechanisms, you try to kind of make it a bit more abstract and quantify it via numbers. And then you start to do like numerical modeling and things like that, which is also like for me, it was always very basic. I'm not a modeler per se, so I guess there's modelers out there who can tell you tons of more things about it. But yeah, that's kind of how I would see it. And coming back to the ocean, I'm not quite sure if there's really a reference system because, and I'm also not quite sure if there would be a value in a reference system. Like um, like in the atmosphere, you have, for instance, like temperature gradients, that's kind of stable, or where you know how it should be, and then you can kind of, see how it develops. What does it mean for weather? What does it mean for fluxes? In the ocean, you have, yeah, okay, maybe you have this overall picture of like, global currents that are there, this thermohaline circulation basically. And the name already says it. It's temperature driven and salinity driven basically. But then you have a lot of local aspects as well that are important. And here we can come back also to coastal areas, because coastal areas are, as I said before, very narrow, but they are very productive. So they are disproportionately important for the CO2 uptake of the ocean in general. So despite covering only like 8% of the area, they take up like 20% of the CO2 that is taken up by the ocean annually. So that's a different number there. And so we see they are important, but when you look at them from space, so to say, you can't even really see them because they are so narrow. So, and then the question is a bit like how are those systems that are obviously important represented in global models? Maybe that touches a bit the question that you asked. So it's important to look at all these exceptions of the ideal system, so to say, because they are in this case very important. But of course, as you can imagine, if you have a lot of exceptions, it's also like, a lot of effort to understand all of them. And then it's also a lot of effort to parameterize them to make it, somehow abstract so that you can put numbers into these very like calculation intense global Earth system or Earth system models. So yeah, that's kind of, I think, the difficulty in that area. Kind of
Challenging
Okay,
drifted off
term.
thanks.
a bit, but
No, it was good. The reason I asked is I was amazed that there was, for example, we say the way the composition of the atmosphere is a certain amount of nitrogen, oxygen, CO2, and other gases. Um, and I hadn't realized this till I was talking to a colleague that came from sort of the marine sciences area in the past, and he was saying there is actually what's known as reference seawater. So they go to a specific spot in the ocean and they collect a certain amount of seawater, and I couldn't tell you what that what constitutes that in terms of what the factors were that they were looking at. But there is this reference seawater that they're using in other experiments, obviously not in the ocean, but elsewhere, and maybe for probes or other things to measure salinity or other elements like this. But when I was thinking about that, I was wondering, for example, this continental shelf, I don't know if that's always, I know in the ocean there's certain layers, maybe defined by temperature or, other ways that you would define that sort of depths of the ocean and the behavior of it. And I was curious if the consistency of the ocean, the temperature profiling, the roughness of the waves, these sorts of things, if there was a reference. So is it always when there's zero wind and there's no sea or swell? Is it, a certain constituency and you need to therefore be out a bit further from the continental shelf? And that was kind of where my question was going. But anyway, you've answered it, so I appreciated the points that you raised. Thanks.
I hope I could answer it a bit. But the question about the waves is actually interesting because waves, I mean, we do have always waves at water surfaces, bigger or smaller, but it's for the sea air gas exchange, it's also important like how these waves look like, if you want. There's this term like called white capping. So, it's basically when the wave breaks and starts to form foam or, sea spray and bubbles and stuff like that. So, and then you have like this white caps on the top of the waves. And in these white caps, you have like this, I always picture it a bit like this. It's like a very blurry zone between water and air. So, and it's a very nice spot for gases to exchange, so to say. But it's not, I'm using the term gases here, but it's not for all gases the same because gases are, some gases are better soluble in water than others. So if you have a gas that is very good, very well soluble in water, so to say, they usually don't rely on this foam or white capping effect because they would anyways dissolve pretty good. But the ones that are hard to dissolve, for them, well, I always talk about it as if it was a person for them. but for them it's kind of good, or depending, I don't know, if you're a gas, maybe you don't want to be in water, you want to be in the air. But no, but it's easier than to be dissolved in water if you have this white capping. While, as I said, for the other ones that are anyways nicely soluble, it doesn't really make a difference. So under certain conditions, certain gases may dissolve better relative to others, while under calmer conditions, the more soluble ones probably dissolve better. But in the end, if you give it enough time, so if you would put a glass of water anywhere, where you obviously don't have really a lot of waves, like visible waves, at some point you would have an equilibrium for each of the gases, depending on their solubility and the partial pressure in the atmosphere, temperature, salinity in the water, and everything. So yeah, that's kind of why waves are also a very relevant factor, and especially the white capping of these waves, which then also kind of relates to the questions, because obviously you have also a lot of breaking waves along the coastlines. So, and how does that affect sea air gas exchange then? And I think that's also like a quite recent topic in science in general at the moment as well. Yeah.
So is it better for carbon, for example, to have this white capping, or is it, do they dissolve easily when it's not? I'm curious, or do we know?
You probably mean carbon dioxide, but because I mean methane is also a greenhouse gas,
Sorry,
has also a
yeah,
carbon in
yeah,
there.
carbon dioxide. Sorry, yeah.
Yeah, well, it's always relative, yeah. So if you compare it to a gas that's more soluble, then the white capping is relatively more important for CO2. If you can refer it to a gas that is less soluble, then the white capping is less relevant for CO2 compared to that gas. So I don't think I would hesitate to give a definite answer.
Okay.
But it's
And
definitely important for the CO2 uptake or exchange between the water column and the atmosphere. And it's also hard because it's different media, right? So in water, you have obviously water, and you have air, which is obviously not water. And then kind of explain like how, or quantify the transition of this gas from the water into the atmosphere, or from the atmosphere into the water, which is usually done by, or it's a common method to record concentration profiles of a certain gas in the water column. So you have a gradient of concentration, which can decrease with depth. It can also increase with depth, depending on which direction the flux is going. And then you use the so-called gas transfer velocities, which basically are a measure of conductance, so to say, maybe. Some people out there might disagree now and would like to explain it differently, but I would see it in this way: how well a certain gas under certain conditions can penetrate this border between water and air, so to say. And then you basically multiply that with the concentration gradient that you have in the water column, and then you get your sea air flux, which is then a calculated flux, which is nice for modeling, because it's something that it's just um, one value that you apply. But then, of course, the question is that always the right value to take, and which value to take under which conditions? So if you have now a lot of white capping, for instance, you obviously have an enhanced sea air gas exchange. So is then a different value, like there's different ways of calculating these gas transfer velocities, is there maybe a different way, a better way to use it under these conditions, and these are kind of questions that create uncertainty in the entire understanding of how much, in this case now, CO2 is being transferred between water and atmosphere. But it's important to talk about it and to look into this. This sounds like a very niche topic, which it is, but it's not a very niche interest. It's actually a very global interest, because these gas transfer velocities are being used a lot in models to account for the uptake of CO2 in the water, in the oceans, which are relevant for the global CO2 or carbon cycling, and the CO2 amount of CO2 that you have in the atmosphere as well. So we do have an interest, especially in the times of global warming, to understand how much carbon dioxide is being taken up by the system really, and how big is our uncertainty, and can we narrow this uncertainty down to have better predictions, which helps also decision makers to calculate a bit better and more accurate.
Yeah, definitely. And through this discussion, I've been kind of reminded of another topic that I wonder whether it makes sense to discuss here that fits into this, which is around carbon pumps, right? So we've talked about a little bit sea gas exchange and how white capping can make that more efficient or less efficient depending on what gas we're talking about. But when we're talking about how the carbon dioxide is stored or brought into the sea, there's a couple of different types of carbon pump, right? And I think those are worth looking into just at this stage.
Yeah. Um, so very general picture. That's also something where you can easily say something in an odd way, so other people, perceive it differently. Um, but like generally, as I already explained in the very beginning, you have this biological carbon pump, so to say, where you have phytoplankton, but also other photosynthetically active organisms, so primary producers in the water column that take up CO2. They assimilate it basically, and then obviously they take it out of the water because they are in the water. So it's kind of a chain reaction. You have this organism, it takes it out of the water, so the water CO2 level drops relative to the equilibrium value that it should have with the atmosphere above it. So it forces the CO2 to gas in. So that creates then the flux of the CO2 into the water. Um, and then at some point, I mean, you also have like at some point organisms, die and then or might get eaten by other organisms, and then they're being, yeah, on the one hand or in the other way, they're going to be kind of recycled, so to say, which then creates the CO2 that they took up and brings it back into the water column, so to say. So you have this constant cycle. So you have this, as I said, kind of closed cycle. So as long as you have this cycle running, you keep the CO2 in this cycle. But what you actually really interested in is, like long-term storage then, for instance. You can have some like calcifying organisms that store the CO2 then kind of in their shells, so to say, and can then store it over long terms also, in sediments or also like coral reefs, for instance,
Okay.
also carbon sinks. But then you also have other systems like seagrass meadows, for instance, and seagrass meadows, especially the Posidonia seagrass, it kind of grows a peat layer, which we usually know from terrestrial systems, like peatlands, but that's the name. And they do have, meters of peat or peatlands on land, but the seagrass meadows of Posidonia in the ocean, they do have that as well, which of course then also stores a lot of organic carbon in these systems. And these are kind of the sinks that are usually referred to as blue carbon because it's like a long-term carbon storage in marine or aquatic systems. And that's kind of a term which I think got a bit more, yeah, interesting or more public over the last years, giving the carbon just colors. You have blue carbon, you have green carbon, you
Yeah.
have black carbon, you have a lot of carbons. Essentially just tells you where this carbon actually is. So, and if we talk about carbon, usually we talk about CO2 in this context. So green carbon would be, for instance, forests or terrestrial
Okay.
plant-based systems, so to say. Yeah.
But interesting that on the seagrass front, because yeah, if I remember correctly, this was a part of your research was around seagrass meadows in Europe. And I remember you telling me a story about how there's a lot of seagrass meadows that are protected now in Europe, but protected perhaps only in theory. And the damage that can be done by people either unknowingly or unwittingly has a pretty big effect on the carbon system that you were describing, right? Since seagrasses are very good at capturing and storing carbon dioxide that they take from the water. What is the effect of protecting them? Why are they so important?
Yeah. So as I mentioned, they are important for the CO2 uptake as well. So they do store a lot of carbon in their peat, basically. But then they are also, of course, like important for biodiversity. We worked a bit in the Mediterranean Sea around seagrass meadows. And there's also these pictures where you really have like, you see the seagrass meadow, and then next to it you have basically bare sand. So it's kind of a desert, and in these deserts you have then the seagrass, and then suddenly you have this entire new biodiversity and ecosystem in these seagrass meadows. So in
Yeah,
this terms, it's also very important. But then it's also important for basically protecting coastlines and stabilizing coastlines, basically from waves, so storm events and such things. So there's like several aspects why seagrass meadows are important, and yeah, they are protected, but then often, like when you like, I remember that we were, for instance, on Elba, like an island in Italy, where we did our research, among others, also seagrass related research. And then you always had, like these boats coming into these nice bays. They are really pretty, these bays, so you could nicely have a nice evening there, a nice night. And I understand that, but then they often put their boats into the seagrass meadows. Probably didn't know that there's a seagrass meadow below, although you could probably tell from above because it's very clear water. You can see what's below you, and then they just put their anchor in there. And when you put the anchor in there and it just gets, pushed around, they kind of destroy these seagrass meadows, and that has kind of severe effects then for the ecosystem, but also for the coastline behind it, so to say, and also for the carbon storage. So yeah, that's kind of a bit of a sad thing. So maybe just raise a bit the awareness here that
definitely.
seagrass meadows are very, very important ecosystems, and they are also very beautiful. So if you have the opportunity to snorkel or dive or whatever, just drop by and pay them a visit. They're
Take
very
a
nice.
look.
It's also just really nice to see how they move. I always like, it's very calming.
Yeah, moving in the
Yeah.
waves.
Yes.
Yeah, and right with that point around dropping the anchors and such. So not only do they destroy the seagrass, which has a very important value in this gas exchange process we've spoken about, but did you say also that they can destroy the peat underneath as well, which has an even bigger effect on the amount of carbon dioxide that can be released back into the water and then back into the air potentially as well?
Yeah, there's certainly other people who can tell you more about that, that were more involved in why these seagrass on top kind of protects the peat below. But yeah, kind of the baseline is that removing the seagrass from and then have the bare peat kind of how do you say, makes it
Opposed,
available.
perhaps.
Yeah,
Yeah,
oppose. Yeah, was right. Huh? Yeah, oppose it to like degrading organisms and then release the CO2 back into the atmosphere, which is basically the process that I just explained before. When you have, organisms taking up carbon and then they're being whatever eaten, or they die and are being, I don't know, remineralized or whatever, then the
yeah,
CO2 gets released back into the atmosphere, then the storage is gone, right? But we do need the storage because we release as society CO2 from like fossil storages, so to say. So we need to refill the storage at a different point, right? But you can't release
exactly.
all storages because then we don't have any storage anymore. I think that's kind of very intuitive. So yeah,
Definitely so.
just
And
around that. Yeah.
yeah, and I think maybe that brings us at this point to our fun fact of the month, which Richard and I have been introducing over the last couple of episodes, and it links very nicely to seagrass in this sense, is that, and I think this is kind of wild to think about, that the amount of CO2 or carbon dioxide that is drawn into seagrass systems from the water is, and you have to correct me here if I'm wrong, Fabian, but 0.63 petagram per year. And this petagram is a unit that I didn't know in tons for those of us that are not used to working with petagram. That's 630 million tons of CO2 is drawn from water systems into seagrass each year. And to put that into perspective, it sounds like a big number. It is, absolutely. But the global CO2 emissions that we created as a society in a year is 38 billion tons. So seagrass is really, really important for working as a carbon sink, but it's a relatively small amount still of the total CO2 emissions. And I think that comes back to what you were just saying, Fabian, around the amount that can be put in, but also we need to think about carbon sinks generally so that this imbalance doesn't go one way more than the other.
Yes. Yeah, it relates nicely. It's also a really very nice number. Um,
It
and
is.
I just want to give a different perspective as well because I have another number which I really do like. It's also gigatons. So, which is the same as petagram. So maybe if people feel more convenient with tons, they might feel more convenient with gigatons instead of petagram. It's the same. So I'll give it now in gigatons because I forgot to convert it into a billion of tons or whatever. And I don't want to do the math now in front of everyone because I know that I will fail with that. So when I was like doing my master's and bachelor studies, where we also had climatology modules and meteorology courses, we learned that the atmosphere back then, that was between 2014 and 2020, somewhat around that, probably in the 2014 region more, had like 750 gigatons of carbon dioxide basically in the atmosphere. And back then we learned that per year via fossil fuel 6 gigatons of carbon dioxide were added. And now I kind of looked up this number again, and I read that we are actually at 880 gigatons of carbon dioxide in the
Oh,
atmosphere at the moment. And then I tried to convert it back by calculating it back. So taking the 6 gigatons per year from 750 in 2014, so now we're 2026, which is 12 years. Let's say 10 years because I'm not quite sure about 14, 16 or whatever. So there would be 60 gigatons added over the last 10 years if you take that calculation, then we would come up with 810. But apparently we're already above it. So it's not only that we are still increasing, but we're increasing the increase at the moment as well, apparently.
yeah.
So, and I thought that's also a very nice number, just to know. And maybe a
Yeah,
fun fact on the
absolutely.
side: same amount of that CO2 is also in the organic carbon in the ocean, so it's easy to remember. Yeah.
And I think that's why this whole topic is interesting to talk about when you put it into context, right? That it might be for some people listening, and certainly at the beginning of this, and they're thinking, what is sea air gas exchange? Why is this relevant? But talking about how the oceans can take in some of the CO2 that's in the atmosphere and how different organisms and different systems can store it is more important perhaps than ever now when we talk about these increases in atmospheric CO2 is how do we store it? Forests are the thing that everyone likes to talk about, and they are certainly important, but I found it super interesting when we were discussing this that how much more important the oceans are as CO2 sinks, and we still don't understand them very well, right? That's why this research is interesting, and I guess why your research was also very useful, and those that you know that are continuing to do it, because this is a complex thing to understand with many different facets to it, and there's still a lot more that we need to find out.
Yes, I agree. I mean, obviously, I really like marine systems,
Yes,
and I think it's really exciting research that you can do there. So if there's people out there who consider doing research in that area, I strongly encourage them to do that. It's very important and it's very interesting, and there's so much you can learn around it.
maybe we'll leave it there for today. I'm looking forward to hearing questions from you, our audience, on this and hearing your comments. So remember to like and subscribe. Throw your comments at us. We'd love to discuss them, and maybe Fabian have you on for another episode where we can look at some of those questions and comments that we get from our audience. This episode is obviously the first one also that we've managed to get onto Spotify. So make sure to follow us there so that you don't miss any episodes coming up. And thanks again, guys, for your time today. Fabian, really appreciate you coming on. It's been a pleasure to have you and to learn something about a topic that I really didn't know anything about. So thanks.
Yeah. Thanks for having me again. It was very fun to talk with you and have very nice conversations. Also, conversations going off a little bit, but guess that's always fun if you have spontaneous discussions. So thanks a lot, and
Absolutely.
I'm looking forward to another episode.